My name is Răzvan. I am the technical leader and the programmer of team 24033 Alphatronic. This season, we experimented a lot. We've tried new things. We done mistakes. We fixed them. Other mistakes appeared, and today we chose to talk about something again, as I've said, iterated on a lot, which is motion control and loop time optimization. As at least last season, we had some subsystems that were quite sensitive to it and needed a high refresh rate and a very precise motion control. I think we have a lot of things that we can share with you guys that helped us a lot, and again, obviously increased our consistency and helped us achieve a great performance. So obviously, as most of us know, the PID controller is the best way to do a position control on any subsystem. We didn't try Squid or any types of controllers. However, we've talked to other teams who tried using those and arrived to the conclusion that this is the best. However, only tuning a PID controller and not doing anything on top is not enough most of the times. So we'll always have some sort of gravity or some friction, which will not be linear. And I have this great analogy that someone told me. So imagine you are on a boat and there are a lot of waves. And if you try to walk forwards, it will be very hard for you. However, when there are no waves and everything is, I mean, nothing is moving, you'll obviously be able to have a better path in terms of that. So that's why we need to try our best to eliminate these forces and make our subsystem feel the same at all points in terms of all angles, all extensions, depending on whatever you have. So we'll walk through a few subsystems and how we managed to achieve great PID control. So let's start with lifts. For lifts, upon just the PID, we also use feed forward. So we have a certain power, which is always applied to our slides in the upwards direction because gravity is acting downwards in order to, as I've said, have better following. So we have two options to do that. We either use one feed forward value at all heights for our subsystem, or we can go one step further and have an interpolated lookup table, which I'm going to show you in the next slide, with corresponding feed forward values for each height. And by doing that, you can also have a certain method in order to also counteract friction and not only gravity. And obviously, if you have counter springing and tensions are different at different heights, you obviously one feed forward value is not exact, is not does not feel the same at all heights, and will in many situations will actually give you worse control over this. So we can use what we used because, for simplicity, we use the FTC-lib interpolate class, which basically allows us to create interpolated lookup tables where we give more steps. You can see there loot.add is the function, and we give an input and an output, and it creates a sort of table. And between all of these steps, there's a linear regression going on. So you don't only provide an initial and the final value, you can provide as many values as you want. And in between, you'll have the linear regression. So for example, on the right, I have the table we did for our lift. We had the max was 60,000 ticks. You can see that the minus 100,000 and plus 100,000, we added them because if the encoder is, I don't know, for some reason drifting a bit, or obviously not always be zero, it might be minus 100 or 60,100 or something like that. You'll get an error that your whole table is out of bounds. So you'll not use the last value. It will just give you an error. So make sure you add that, and you are always, no matter what happens within the boundaries. Obviously, you can override this the value that you get from this table and add an if statement in order to counteract this, but we did this because it was easier. So yeah, you can basically what you can do for lift and what we did more or less is I know have 10 heights, let's say, or 10 intervals, and at every interval find a value that just moves the lift upwards by very little, and then subtract a constant for it, so that this way you I don't know you're sure that your free for value is not lifting the subsystem and is just maintaining it at the desired height, but also making counteracting friction and tension, which is different at different heights. So that, for example, as you can see, as we were raising our lift upwards, our F value would increase. So you can see it's 0 until 25,000 because we also have counter springing, which is only in continuous. So more than a slide, it doesn't do much. For arms, this is a picture of our robot in June, so before a few upgrades, 2024 from center stage. For arms, you obviously, when it is parallel to the ground, you need the most amount of power in order to hold it. Whereas when it is upright, as long as everything is good with your subsystem, it doesn't need any power in order to maintain its position. So we can use our cosine function to help us. So because cos of and yeah, have it working well. What we also did, because we had a pivoting slide, I mean, one module, let's say, this teams for like Eastern Foxes and many other teams this season have slides on the left and on the right of the arm. We had only one in center stage. We didn't need uh, that there are so many. So what we also did is to actually calculate the feed forward value for the lift. We use the sine function as when the lift is parallel to the ground. So basically an extendo. You don't need any feed forward component, and when it is upwards, you need one. And yeah, based on the angle, which is 0, 90 degrees, maybe goes all the way to 180. If you're using the sine function, this part will get updated. And because you're also extending the whole the slides, the feed forward value for the arm will also change. So you can run a simple linear regression on that. And here, when it says cos angle times kf, you can also have a multiplier, which is 1 when it is fully retracted, assuming you tune your kf, your f value when it is retracted, and another one when it is fully extended. Obviously, you can make an interpolation lookup table and have more intervals, but I don't think it's needed. And this is what we did last season, and we had very good control of our arm. However, it was a bit sensitive to loop times, and I will cover them soon. For extendos, you can do the same as we did for lifts. Take a value that would barely move the subsystem and subtract a constant for it. And yeah, at every extension, you should have the subsystem should feel more or less the same. And yeah, it should be fine. Obviously, when you do all of this, you need to have a way to compensate it for voltage, because your voltage will change across the match. Maybe you're also moving the drivetrain while you're moving the lift, or you're not moving the drivetrain when you're moving the lift. So your current draw will be different. So as long as your subsystems are not overloaded, maybe your drivetrain you use 1150 motors on your drivetrain, not without any gearing, and it draws a lot of current and it can't really move it. Yeah, you shouldn't probably use this. I've heard that some teams had some bad experiences with it. So again, you need to test it, but those values that you tune for K static or feed forward need to be somehow compensated, or I don't know, you can tune them at when the battery is fully charged, and when it is halfway charged. It's up to you, and again, you need to test. And yeah, you can see here the formula that the power that we send to the motor, to the lift motor, which is just the calculated PID power plus the feed forward one, and everything times 12 divided by the voltage. It is normalized, it is compensated, because so that If our voltage is 13, we get less power, but if it is 11, we get more. With PID coefficients, it's very important to know that the a set of PID coefficients on, let's say, 100 hertz will not function as well on 50 hertz, because the rate at which power is updated is different. So maybe higher refresh rate, you can push your coefficients to be higher. However, when it is lower, it might be more shaky. So what we also did, but again, it depends on the loop times, because above a certain value doesn't really matter. You can tune two sets, one for teleop, one for auto, in order to have a consistent performance. And why we have lower refresh rates in auto, it is because we also need to read the odometry, the IMU, every loop, and that takes a lot of time. Another thing you can do for motion control, which helped our drivetrain a lot, is add some way of deceleration, either through a motion profile or through what we did, which is a predictive localization. Basically, we calculated where our robot would end up in if power is cut, and use that code in our PID to point values, PID to point calculations. And basically, the robot would come to a stop earlier, but while coming to a stop, the predicted pose will be closer to the actual one, so it can just arrive to the desired target without stopping abruptly, wheel slipping, having to correct again, having overshoot, and all other external factors that are not in our control. Finally, a few things about loop time optimizations. There's three things we're going to cover. The first one is motor power and servo position caching. Wherever you call set power, set position, you make a hardware write. However, if you already set the same power the last loop, then why set it again? So we use wrappers that you can find, I think, from Mercurial or Dairy FTC for it. And if the motor power is within a threshold, or the position is within a threshold of whatever you think it's enough, 0.02, 0.005, depends. Also, our thresholds for motors that we have an interpolated lookup table for are obviously lower, so they get updated more times. But again, if the value is the same, then it's not needed to set that position again. You'll want to bulk read your hubs in order to have only one read for the sensor and not one read for all sensors and not one per sensor, except I2C sensors. We use manual and clear the cache manually at the start of the loop. We have more control. We don't use auto because who knows when the bulk cache is cleared. So we use that. Try to only cache the control hub and put all your servos, drivetrain, important servos, drivetrain motors, and sensors on that, because the hardware write and read times are a lot better, and use the rest for the expansion. We bulk read both because we call the current sensor from motors which are on the expansion hub, and we use the ease over current function because it's better for our refresh, and that is bulk read. So we must bulk read both. And finally, as you probably know, I2C sensors take a lot of time, so you need to be very cautious about how you pull data from them. What we did from the start of the season is having a dual sensor intake. Have two sensors on our intake, one which is digital and it doesn't affect loop times, and a color sensor which only checks the color and only makes three reads and makes an average. And this way, we don't have to call an I2C sensor to know if a sample entered our intake. We just call the digital one, which is a lot faster and takes less time, and makes the whole process faster. And again, having better loop times means you have better PID control, and everything works out well. And for our when we score, we use the IMU in the hub, the pinpoint, in order to auto align our turret to the basket. And there isn't a need to pull data from the pinpoint if we're not scoring. So we only update the heading when we are scoring, because even if you don't call the update heading function from the pinpoint SDK, it still tracks it. So there's no need to call it and update it when you are not using it. So that was those were some things we learned throughout this season that helped us achieve a very consistent performance in throughout all the matches. And yeah, thank you for having us in this edition. And we look forward to any questions. If you do not have time to address your questions today, you can contact us on Instagram, Discord. You can find us on pretty much any social platform. So thank you.
Yes. That would be excellent. Thank you so much. Let's give a round of applause. So it looks like we have time for one online, one in-person questions. So someone online asked, at what point do you implement, if PID is good for beginners? And yeah.
Let me think. Usually you'll want to use PID. I mean, it depends on the robot, obviously, but I think it's not that hard to learn it if you actually know how it functions. Obviously, PID 2 point for drivetrains or other subsystems which have more than one axis of motion is a bit harder, and maybe I suggest using libraries which are very good, like Pedro Pathing. For arms again, and other maybe you have other subsystems, it's a bit tougher. But for lifts, extend those. I don't think it's is that complicated. You have the community on Discord, and you can ask as many questions as you want to learn more about it. And using videos on YouTube where you learn how to tune a PID controller, the things that I presented this presented in this in the slides. I think you can achieve very good control of any subsystem you want, and not have a very hard time doing that.